Hello, everyone. So you're welcome to this lecture. Here we want to start looking at homomorphisms and isomorphisms. Really, isomorphisms to be exact. That's what we want to look at. In the last lecture, we looked at what a binary structure is, and we said that isomorphisms basically helps us to be able to tell whether two structures are alike structurally, right? So that is basically the motivation for isomorphisms. So we want to define what a homomorphism is, right? Let G and H be groups, okay? So they are groups, and let phi here, this function here, mapping G to H be a function. Then phi is called a homomorphism if for every A and B in G, we have that phi AB is equal to phi A multiplied by phi B. Okay, note that AB here, I should, okay, so I could use this to show that. So in G, for example, if you take any element A and B in G, the operation of A on B is basically based on the binary operation in G. Phi A and phi B are elements in H, okay? So the product of phi A and phi B is based on the binary operation here. Okay, so we don't bring the binary operations, but you should have that at the back of your mind that they could have different binary operations. Okay, G and H could have different binary operations. Okay, so here AB basically is A star B, right? If you use this as an example, whereas phi A times phi B is phi A star prime phi B, like that. Okay, so but basically to say that something is a homomorphism is basically because of this relation, right? If you are able to show that, let me pull out my listing here. If you're able to show this, then that is basically the idea of a homomorphism. Okay. Note that a homomorphism does not have to be one-to-one. We'll come to that later on. Okay. Basically, if I have a function from one group to another group, these groups could have different binary operations, but if I'm able to show this, right, then I have shown that a function is a homomorphism. So that is what a homomorphism is. Okay, so we'll use this a lot. So keep this in mind, the definition of what a homomorphism is, because we'll come back to it over and over again. Okay, good. Let me go on full screen here. Okay, good. So that is a homomorphism. All right, what did I put here? Right, they could have different operations. Good. Now let's look at this example here. This is a simple example. Let F be the additive group of all functions. So this contains functions and you can add them up, right? We know how to add functions. Mapping from the real numbers to real numbers, and let R be the additive group of real numbers, and let C be an element, right? C is some number in R. Define the function phi underscore C from F to the reals by this. Okay, so this is how we define our function. Okay, so I will need to get out of this again. So we have let me get this. So it is defined by this, right? The function phi underscore C is given by this. So it takes in a function, and the result is plugging the C here into the function that it takes, and that gives you the value, right? Your final value for it. So basically, that's the definition of this function here, which takes elements from F to R. Okay. Now let G and H be elements of big F. We want to show whether this function here is a homomorphism. That is the point of this example. And remember the definition, right? To show that it's a homomorphism, we have to show this. In this case, the operation is like a star or star prime or something. But in this particular case, this example, our operation is addition, right? So it's going to be A plus B, if you like. It's going to be phi A plus phi B, because the binary operation in this case is addition, okay? So we want to take phi C and take two functions, G plus F. Well, by this definition here, this has to be equal to G plus F and plug in C, right? By this definition of what phi C is. So this gives us that. But of course, we know that to add functions, you have to, G will have to work on C here, right? Have to take G of C plus, oh, actually, this is not, we're using F here, I think. So let's just stick with F. So this is supposed to be F. Okay. So this is, let me correct that. So this here, this is FC, right? FC. Okay. So you get that. Okay. But GC actually by this definition is G underscore phi underscore CG, right? By definition. And this guy here is, this is funny. Okay. So this guy here is phi underscore, so again, this should be F, right? This should be F here. So phi underscore F. Okay. So we, so this shows that if I take, this is the same as saying that if I do this, if I take phi, if like underscore C of two elements multiplying, I get phi C of A, phi C of B. In this case, the operation here and then here is addition. So there's addition here and then there's addition there, right? It's A plus B, in this case, phi of A plus phi C of B. So that is what we have shown here. So this actually obeys that. So therefore, phi of C is a homomorphism. You see that? Okay, good. I'll correct these typos, right, before I send you the slides. So this proves that this function is homomorphism because you can do this. Okay, good. Now let's come to isomorphism, right? The big brother of a homomorphism. What is an isomorphism? Well, let the function phi that takes elements from G to H be a homomorphism, okay, where G and H are groups. Well, then phi here is called an isomorphism if it is one-to-one and onto function, right? G, in that case, if phi here is an isomorphism, then G and H are said to be isomorphic, okay? They are isomorphic to each other. They are structurally alike. That is basically what it means, okay? So they are isomorphic, which is denoted by this symbol. Well, sometimes instead of the double equal sign, sometimes this symbol is also used. That doesn't look nice. Sometimes this symbol is used, right? You have that symbol and then one, okay? Just one straight line underneath F. Sometimes this is used as well. Okay, so first of all, if you have a function from a group to a group, that function first has to be a homomorphism. And then if it is one-to-one and onto, right, then you say it is a homomorphism. In other words, the relationship between from G to H here, right, is a one-to-one function, is an onto function as well. So you have to keep going back to know what an onto function is and what a one-to-one function is, okay? So it has to be a homomorphism, and then you add the extra two conditions that it has to be one-to-one and onto. So keep that in mind because we'll use that to prove some theorems later on. Okay, good. So okay, so here are some definitions that you can take note of, right? When you have a one-to-one homomorphism, remember that a homomorphism does not have to be one-to-one. Homomorphism basically means that I can do this, right? I can do AB is equal to phi A times phi B. That's basically it. So it doesn't have to be one-to-one. But if it is one-to-one, then it is called a monomorphism here. And an onto homomorphism, right? If it's a homomorphism and at the same time it is onto, not one-to-one, it's homomorphic and onto, then it is said to be an epimorphism, okay? Now a homomorphism from a group to itself, right? So the function is moving from G to G, okay? It's called an endomorphism. Remember, normally it is from G to another group H, right? So if it's from G to G, then it is an endomorphism. And an isomorphism from a group G onto itself, right? It is an onto function, all right? It's called an automorphism, all right? So these are sometimes these, you may come across it somewhere. So these are the differences between them. Okay, good. Let's move on to this. So basically, this is an important theorem that we want to prove. We'll prove just this theorem, and I'll end the video and come your way again to with another theorem, basically for this section of isomorphism. This is a bit lengthy, so we'll finish this and then we'll come back to another one. Okay, this theorem says that let G, H, and K be groups. All right, they are groups, and let phi here be the function that maps G to H. And psi here is a function that maps H to K, all right? If phi and psi, these two functions here, are homomorphisms, okay? You know what that means. Then psi of G, or psi times G, this is a composition, right? The composition of psi and phi from G to K is a homomorphism, okay? Remember that it has to be from G to K, right? Because remember that a composite function, this will have to act on its domain, right? Phi will have to act on its domain to give you something in there in its codomain, and then psi will have to act on the codomain of phi, right? Psi takes values from H, which is the codomain of phi. So keep that in mind. So that is why it is from G to K. Okay, so you want to show that this composite function here is a homomorphism. Okay, secondly, if psi and phi and psi are isomorphisms, okay, then the composite function psi of phi here is also an isomorphism. And finally, if phi is an isomorphism, then the inverse, right? The inverse, which takes elements from H to G, is an isomorphism, right? Phi takes from G to H, so the inverse will have to take from H to G. Okay, so this is an important theorem that we want to prove. So we'll prove it, okay? And then we'll end the video after that. Okay, so how do we prove this? Both this and this homomorphisms, all right? So we know what that means. You can do, right? If you go back, basically you can do this. That's what this means, okay? For both phi and psi. If there are, but we want to show that the composite function itself, all right? Not just the individual functions. The composite function, it's a homomorphism, okay? What does that mean? Well, remember that this composite function to be a homomorphism, okay, for the composite functions, if you like, psi of phi to be a homomorphism, then if I take an element, if both of them, right, if this guy, if they take some AB, right, I should be able to write this is equal to, right, psi of phi A times, right, times, usually we don't put any operation, right, and then psi of phi operating on what? B. So to show that the composite function is a homomorphism, really what I want to show is this. I want to show that psi of phi product A product B is equal to that. Okay, once we are able to show that, then of course we've shown that it is a homomorphism. Okay, then we'll move on to show that the composite function is an isomorphism. Okay, so let's look at the first one. Well, let G, H, and K be groups. Of course, we are given this information from the theorem. Suppose phi and psi are homomorphisms. We are given that information as well. Now let A and B be functions of G. Okay. Remember that G is the domain of the composite function. So let A and B be elements of G. Then psi of phi in G in AB, right? If it takes this is equal to, right? Because it's a composite function, we can write it as that, right? Good. Now, because phi here is a homomorphism, we can split this into that. Okay. Also, psi is also a homomorphism, so it takes this multiplied by its value on this, right? So we are going to get psi of phi A and psi of phi B. Okay, but remember that this is actually the definition for the composite function. All right, this is also a composite function on B. Okay, so you have the composite function psi of A, psi of B. All right, and that is really what we want to prove. If I take psi of B, phi psi, right, the composite function takes AB, you can split it into this following this approach. This basically shows that this composite function here is a homomorphism. Remember, this is what we really want to show. Okay, so we have shown that here. Okay, that means that it is a homomorphism. So we have proved the first part. Okay, now the second part says that we need to prove that the composite function is also an isomorphism. All right. Well, what is the difference between them? Well, first, to have an isomorphism, it has to be a homomorphism. Secondly, it has to be a one-to-one function. And thirdly, it has to be an onto function. Okay. Not in that order, right? So first, we're going to prove that, well, we have already shown that it is a homomorphism. So that is gone. We are fine with that. So we need to prove that it is an onto function. This guy is onto, and also that it is a one-to-one function. Okay, so that is what we need to prove the second part. Okay, good. So here's the proof for that. Now, suppose these are isomorphisms. We are given that in the theorem. All right, they are isomorphisms. From the first part, we know that the composite function is a homomorphism. So that is good. Now, since psi here is an onto function, note that psi takes element from H to K, right? So keep that in mind. Psi is taking element from H to K, whilst phi is taking elements from G to H, okay? Good, so keep that in mind. Now, since both phi and psi are onto functions, it means that it's onto because if I take any K here, I can find some H here such that phi of H is equal to K. That's what it means to be onto. Okay, so since this guy is onto, if I take any K in K, there exists some H in H here such that phi of H is equal to K. Okay, also psi here, or phi, I should say, phi here from G to H is an onto function. Also, that means if I take an H here, small h, all right, I can always find a G, small g, inside this such that phi of G will give me H. Okay, so also since this is onto, I can find a G in big G such that phi of G is equal to H. Okay, so these two conditions, we'll use them. They're important. Okay, and that is because both of them are onto functions. Now, to show that the composite function is onto, we should be able to say that to take elements, see, the composite function takes elements from G to K, right? To show that it's onto, we must show that taking any K here, I can always find a G here, so that if the composite function acts on the small g in G, I get K. If I'm able to prove that, and I have proved that the composite function is an onto function. Okay, so that is what we want to do here. So here, let's take the composite function, plug in G, small g, in its domain, capital G, right? If you do this, I can rewrite this as that by composition, right? Now note that phi, right? Phi of G here is H. So this becomes H, right? but psi of h is equal to k. Psi of h is equal to k. What this means is that if I pick any k, right, in the codomain of the composite function that is here, if I pick any k, I can always find a g such that here, composite function on g will always give me k. Okay, so this goes to show that the composite function is an onto function. Okay, it is an onto function. Good. Okay, so we have shown that it is onto. The next thing to show is to show that it's one-to-one. Once we've shown that it's one-to-one, then we have all the ingredients we know to conclude that it is an isomorphism, right? Good. So now to show to show that it is one-to-one, you know how we show one-to-one, right? If something is one-to-one, then for instance, if the function f is one-to-one, then f of x is equal to f of y implies that x is equal to y. All right. So if if f is one-to-one, then the argument of f here must be equal to the argument of f there. Okay, good. So that's what we're going to use. So suppose you have x and y in G, and then the composite function on x is equal to the composite function on y. We can write this as a composition, right? Phi into phi of x, psi into phi of x, psi into phi of y. Okay, note that psi here is a one-to-one function. Therefore, the arguments must be equal. This has to be equal to that, right? Because psi is one-to-one function, so get this. Also, phi is a one-to-one function. Therefore, x here must be equal to y here. This has to be equal to y. That goes to show that the composite function is really a one-to-one function. Okay, so it is one-to-one, it is onto, and in part one, we showed that the composite function is a homomorphism. So with these three ingredients, we can conclude that it is an isomorphism. Okay, great. So that is the second one. The third one is straightforward. Okay, so the third condition we want to prove is this. If phi here is an isomorphism, then its inverse, right, from H to G is an isomorphism. Okay, well, to show that, again, to show something is an isomorphism, first it has to be a homomorphism, and then it has to be one-to-one and onto. Well, one-to-one and onto is easy because if the function phi itself is one-to-one and onto, which it is because it's a homomorphism, because it's an isomorphism, we know that phi is one-to-one and onto. Therefore, its inverse has to be one-to-one and onto as well. So that is given. So that is easy. So the critical thing to prove now is to show that phi inverse here is a homomorphism. Okay. So basically, we want to show that phi inverse. If I take phi inverse of AB, for instance, I'm going to get phi inverse of A times phi inverse of what? Of B. Okay, so basically this is the main proof that we want to prove, to show that the inverse function is an isomorphism, because the one-to-one and onto part is given to us easily because the function itself, phi itself, is one-to-one and onto, so its inverse has to be. Okay, so what we need to prove, the third one, is this. Suppose that phi is an isomorphism. Well, we know that if phi is one-to-one and onto, then the inverse is also one-to-one and onto. So that is cool. That is fine. Okay. So the next is really to prove this. Okay. The next thing is to prove that phi inverse of AB is equal to phi inverse of A, phi inverse of B, right? To show that it is a homomorphism. Okay. So how do we do that? So, well, if phi inverse, phi and phi inverse, right? Phi operating on its inverse will give you the argument, right? It's the same if I take phi f, right? F into f inverse of x, I get x. So this will give me xy, okay? Okay, but x itself can also be written as this, right? I can write x as phi, I can write x as phi times phi inverse of x. This will give me x. Phi times phi inverse of y will also give me y, right? So this is equal to that. So that is fine. Good. But the next part is based on the fact that phi here is phi itself, not inverse. Phi is a homomorphism. So we can actually group them. Okay. Remember that if phi is a homomorphism, then phi A times phi B, phi of B, is equal to phi into AB. You see that? Often we go from this side to this side, but you can also go this way because it's equality, right? So if you have phi of A times phi of B, you can really group them. You can pull your phi out and you have A times B. So that is what we are doing here. Because phi here is a homomorphism, we can pull phi out and then we multiply phi inverse of x and phi inverse of y. You see that? It's because it's a homomorphism. So we get that. Homomorphism, I should say. Okay, so finally we get that the left-hand side, which is this, is equal to the right-hand side, which is that. But remember that phi is also one-to-one, right? Because it is an isomorphism, right? We are given that phi is an isomorphism, so it's one-to-one and onto. Okay, so since it is one-to-one, right? Phi basically is like canceling out, and then the argument. Its argument must be equal because it's one-to-one. So this guy has to be equal to that guy, right? So phi inverse of xy has to be equal to phi inverse of x multiplied by phi inverse of y. But this shows that phi inverse is a homomorphism, right? Okay. Remember what I wrote here, right? To show homomorphism, this is what you want to show for the inverse. So we have really proved that phi inverse is a homomorphism. Okay, so it is a homomorphism. It is one-to-one. It is onto. Therefore, it is an isomorphism. So the inverse function is an isomorphism. So that brings us to the end of the proof of this theorem, theorem 11. Okay. So go over it. If there is any part of the argument that you are not clear about, doesn't make sense to you, just let me know and then we can clarify it. Okay. So in the next video, we'll look at another theorem. Okay. It's a bit lengthy. That is why I don't want to cover it now. Okay. So next time we come, we're going to look at theorem 13. Okay. This definition, and then we'll try to prove this one as well. Okay. So I'll come your way. I'll stop this one and then come your way later on.